Okay, thank you. Well, welcome everybody. Thank you for coming to our departmental seminar, technical seminar, and it's a pleasure to have here Dr. Chirkova from the computer science department. Dr. Chirkova is an associate professor in the CS department here at NCSU. She received her BS and MS from in applied mathematics from, I'm sure you all know, famous Moscow State University in Russia. And she got her PhD degree from Stanford in 2002. Her research interests are in databases with a focus on query processing. She's received several awards, one of them primarily the NSF Career Award, which is very prestigious. And she served on many computer science-oriented conferences, ACM, SIGMOD, etc. And it's a pleasure to have her talk to us today about her query optimization. And Rada, the floor is yours.
Thank you. Thanks for coming, everybody. I'll be talking about query optimization. So basically, it's a very theoretical approach that can find very practical uses. So we will be talking about so-called relational databases, and I'll give an overview of what those are about, and I'll try to explain why it is important to execute database queries faster, especially in data analysis context. And we will see how you can help evaluate the queries faster by basically providing different definitions for the same query. And I will argue that the results that we will be discussing are directly applicable at the practical level, and again, especially for complex data analysis queries. So this is basically what the talk is about in a nutshell. And let's just start. It's a very old slide, and so when I showed it 10 years ago, that was true then. We are awash in data. It's that much more true now, and basically all companies that sell things run on very large databases. And people do analyze data for practical purposes. And one very common accepted format of storing the data that gives you tools to analyze the data is so-called relational databases. And you see a typical icon for relational databases here. So how are data stored relationally? It's very intuitive for people to understand how data are stored relationally. It's just tables. And so that's what the users want to know about the data. So here we have some storage, typically on disk, of very large amounts of data. The user wants to know that this data is formatted as a table. Very natural, very simple. So for companies that sell stuff, it is typical to store information about transactions. And the name of this table is POS because this is point of sale transactions. And so for a point of sale transaction, you would want to record information about the item that has been sold, about the store where the item was sold, about the date of the transaction, and also the amount. And so that would be the natural format for the data that you would store in the points of sale transaction table. And here it just gives you basics, basically IDs of things. ID of an item, ID of a store, date is also some kind of ID. The measure of interest is the amount. How much was this item sold for? Now, if you want to look for details about items, for instance, you would look into a different table. So let's say this table is called items. And so for each item ID, same notion as in the other table, you would store the ID of the item, the name of the item, and the category that this item belongs to. And that's all you need to know about relational storage of data. Any questions about this? Just relational storage of data. So now that we know how data are stored, let's look into how companies that produce data processing tools, how do they process data that are stored in tables?
Sorry.
Yes.
So there is absolutely no allusion to what the size of the data anywhere, though, right?
Well, in real-life applications, you would have billions of rows. So a typical example that everybody gives is Walmart, which stores tables with billions of rows. And so the data has to be stored somewhere, and it has to be processed efficiently.
But in your attributes of your data, the size doesn't matter?
That's a very good observation. So what you have here is the size of the description of the data. So basically about each item, you want to store information about the ID of the item, the name, and the category. And real-life tables could be dozens of columns, but the real size of the data is in the number of rows. So the rows go from top down. And so you can easily see how you could generate millions, billions of transactions in very short periods of time. Does that answer your question?
Yeah.
Okay, perfect. So let's imagine this is a data analyst. And one very useful consequence of the data being stored in the relational format as tables is that users can ask English-like queries, very intuitive queries on the data. So if a data analyst wants to say, give me total sales by store ID for all appliances, and the table that she has in mind is this point of sale transaction table, then you have a more or less intuitive way of writing this particular question, right? So what data analysts do is they ask questions like this, and they'll get to this SQL in a second. And so what they want to get is they want to get for each store ID, they want to get the total amount for, appliances, right? So that's what data analysts do. Now, what do database systems have to do in this context? Basically, it's about very large amounts of data. And the data analysts want to get their answers back as soon as possible. And so that's the challenge for database systems. Now, let's look at how the query, this same query, is actually asked. So you have this structured way of essentially saying this thing. You are describing what you want to get from the data. And for the purpose of this talk, it's not necessary for us to know the actual language. It's sufficient for us to know that this is a declarative language where the users just express what they want. Okay? The challenge with queries like this is that very large amounts of data have to be processed. So this is the same query, data analysis query. Let's look into what it involves to execute this query. What is the sequence for executing this query? So first, you compute a query queue, and we will be working with the query queue as a running example. So we want to get all combinations of store ID and amount.
What is quanalysis?
This is my name for this query.
Oh, okay.
My name for this query, thank you. Okay, so I'll be referring to this query, and that's what the data analyst had in the cloud in her mind. So that's the same query. So how do you execute this query when all you have stored is tables? So first of all, you want to compute just the data that is relevant to this query, right? So you have all the data that is relevant to transactions in your database. You want to set aside just the data that is relevant for this query. How do you do this? We call this query queue. So the query queue computes all combinations of store ID and amount for the transactions where the category of the item is appliances, right? So not all stored data satisfy all of those constraints, right? So we put aside a pile of data that satisfies this description. Then you do what the data analysis query really does. It says group by store ID. So for each separate store ID, you get a different pile of this data, right? So you partition this data so that you could compute the amount by store ID. Does it make sense? And then once you have partitioned the data this way, then for each pile you compute a separate sum of the amount. And this way you get the amounts by store ID. Does it make sense? So that's what the database engine has to do to process this query. And the challenge here is really you only want to touch the relevant data. You don't want to look at all the data that is stored in your database because you want this question to be answered as efficiently as possible. So in most of this talk, we will be concentrating on this query queue. Okay, so we're not looking at grouping or aggregation in a lot of detail. Why are we not doing this? Because the main challenge in computing this query would be in putting together just the relevant data. Once you've put together just the relevant data, then basically it's a breeze to do these two operations. So how do you put together this relevant data? So we have a SQL formulation for this query. What this query says is find all combinations of store ID and amount where category is appliances for the item ID that was sold. Okay. Answering this query would be time-consuming on large unordered data. It would be time-consuming anyway because the amount of relevant data is expected to be large. If you look at all the data, then it becomes unmanageable. Okay. So as the more efficiently we can answer this query, the more efficiently we can answer the analysis query. Because the analysis query on top of this is just computing the sum of the amounts in each pile. Right? So we're talking about efficient processing of this query. So that's what query optimizers do. SQL, the language that we use to express queries, is declarative. It doesn't give you a procedure to answer the query. For this reason, relational database systems have so-called query optimizers. What they do is, given a declarative query like this, the optimizer constructs a space of more or less efficient execution plans for this query. And those execution plans are take a table, select all the relevant rows from this table, format those rows, combine them in certain ways, and that's what the optimizer does. So it's very important to find a plan that is as efficient as possible when you talk about very, very large amounts of data. So here's one plan for answering this query queue. So you could look at all the rows in the table point of sale transactions, all the rows, relevant, irrelevant, doesn't matter. The arrow here says that this is not a very efficient way of finding the rows that are relevant to this answer. So then you also look at all the rows of the items table. And again, the red arrow says that maybe you could do it in a more efficient way. Then you select from the items table just the rows where the item is an appliance. Right? Once you have obtained all the rows here and all the rows here, you combine the rows from the two tables on the same item ID. So you basically want to get matching pairs of records. Does it make sense? And so formatting the answer to queue means you just throw out the relevant stuff from each row. Basically, in each row, you keep just the store ID information and the amount information. Right? So this is a brute force way of executing this query. Not good on large data. The red arrows say it's not good on large data. The next plan I'm going to show you swaps these two branches. So this branch will remain the same, but it will be shown on the left side. I'm going to make an improvement on this. Okay? And the only way I can make this improvement is I swap the branches. So let's see how. So this branch is as before. Brute force scanning of the items relation. Keep just the information about the appliances. So what you can imagine in the query processor, what's going on, each row that gets out of this operator is for an item whose category is appliance. So all irrelevant data has been filtered out at this point. So each item ID that gets here is relevant information. So you take the ID of each such item, and then you probe the other table on that item ID. So if you have so-called indexes on the data, you could access a row or rows that have this item ID. So that means that for the point of sale transactions table, you don't access any relevant data. So that's a major improvement, and that's just a different plan. And this is also something that a query optimizer would consider. And then again, you combine on the same item ID, and then you format the answer. So that's already an improvement. Can we do any better? Can we do better on the red arrow here? Yes, if we have an index, again, the set of pointers where you say, okay, give me all the items whose category is appliance. That gives you only those. That means that you don't look at the relevant data in this table either. Right? So indexes are just pointers to stuff where the category is appliance in our case. And so you get just the relevant item IDs here, and then again, as in the previous slide, you probe the other table. And so here you are not looking at any relevant data. So it's much better. It's a big improvement over the previous plans. And actual query optimizers do consider all of those plans, all plans like this. Now the question is it good enough? Because we're still, yes?
How do we get pointers to rows or journal?
This has to be pre-computed data. So you have this table, right? And you say, okay, I'm going to ask a lot of questions on categories of items. And so what this index does, it says, I have 17 categories of items mentioned in this table. So for each of those categories, I'm going to keep a set of pointers to all the rows in this table where this is the category of the item. And this is called indexes, and this is used everywhere in data processing systems, because what it does for you is it allows you to not access irrelevant data.
The only thing is we need more memory for that.
It's all on disk, actually. The indexes are on disk as well. That's how large the data are. And so you have to page indexes, relevant pages of the indexes into memory. That's how large the data are. Thank you. Okay. So the question is it good enough? Because even with the relevant data and with real-life companies, we could have very large amounts of just relevant data that we have to explore. Very, very large amounts. So can you do any better than this? So what do query optimizers do? They work at query runtime. So that means they have very little time to explore all possible execution plans for a query. So the user poses the query, and then the clock starts ticking. First, the optimizer works. And so it has to converge on a more or less efficient plan. Once it has produced a more or less efficient plan, then this plan is applied to the actual data. And so that's all part of the query processing time. Okay? So it works at runtime. Because it works at runtime, it cannot afford to look at the entire stored data. This is unmanageable at query runtime. Okay, so instead it uses so-called statistics on the stored data. The number of rows, the number of values in a column, things like this. Okay? So optimizers are very complex because a lot is at stake in finding an efficient execution plan. And so what we've seen 3 so-called physical level execution plans for the query. That means that the definition of the query is always the same. We've just found several variations of execution of this query. Here's another plan for the same query. Suppose we have pre-computed information about the IDs of just items that are appliances. So that's just those IDs. They're put together. Okay? Just item IDs for appliance. So you scan this information because all of it is relevant, because our question is about appliances. So you scan those item IDs, and then the rest of the plan is the same. So that would beat the previous plan that we saw. So that's desirable to consider this plan in the execution. But something is really wrong here. Something is wrong because this we can't really legally consider in the consideration of this query. That was not in the query. That's something else. A view is you ask a different query. So give me all items that are appliances, and then you pre-compute the answer. So the definition of this query is different. So here's the different definition. What it says is give me store ID and amount from the point of sale transactions where the item ID is appliance. That's a different way of writing it. And
Your touch does affect.
right. Yeah, I see. That has the same effect, right? Mm. So if we have this definition of the query, then that means that our view appliances, which is return all item IDs that are appliances, can be used in answering this query. So that's somehow in the definition. That was not in the original definition. So we have a different definition for the same query. Does it make sense how it would be more efficient to execute? We just pre-computed part of the answer to the query, and we're using this part of the answer. So this query, this reformulation of this query, under certain conditions on the stored data gives us the most efficient plan for executing the original query. So it would be desirable to get this reformulation of the query. And so because it gives us the most efficient execution plan for the query for all pairs of store ID and amount, then it would give us the most efficient execution plan for the Q analysis query. And in considerations like this, how badly do you want the most efficient plan for the query? In my collaboration with a company, I saw data analysis queries that had a 24-hour execution window, right? So you would ask those queries daily on the data, and you would have up to 24 hours for the query to be answered. So a lot of those queries on real data, if they are formulated in a bad way, they would be executed for longer than 24 hours. So a lot is really at stake in finding efficient execution plans for analysis queries. So this is our best bet. How do we get this from the original formulation of the query? So what we see is that this SQL is not identical to the original SQL, right? So I can bring it up. I'll bring it up again. So what we're saying is that we get a different definition. How do we find this different definition for the query optimizer? Because if we don't get this different definition of the query, we will not be able to execute it. The optimizer will not be able to execute it. The challenge here is to get the optimizer to generate this other definition and its efficient execution plan. So here's the query reformulation problem. So if you are given the definitions of two queries, so the original query Q and the QM modification in our case, you need to know if the two formulations always give you the same answers, right? So are they about the same thing? So we want to see whether the two queries give the same answer on all databases. So why are you asking this version of the question? Why are you not just asking, we have this database here. Just tell me if those two formulations provide the same answers on my database. I don't care about the other databases. Does it make sense? The reason we have to do this is that we have this query execution window, right? And we can't afford to look at the data and to analyze the data to see if the two definitions are equivalent on my database. So we have to say, give me just equivalence on all the databases, right? So we're looking for some syntactic conditions that, given just the definitions of the two queries, give us assurance that on each database, those two queries will return the same answer. This is really our challenge. We can't afford to look at the data because we're doing this at query runtime. So we're looking, for some test that, given the structures of the two queries, tells us if they always give us the same answers or not. This is fun, right? Because we're given the syntax, and we are asked whether they have the same meaning. Very interesting question. And so that's what I said. We cannot afford to explore the stored data. So we'll look for syntactic conditions.
Can you get the SQL to run an optimization for how to structure the query automatically?
This is what I'm trying to explore in this talk, right? So we're given a fixed formulation, right? And so we know, given a fixed formulation, how to produce those three plans for this query. What I've tried to argue is that it's not good enough. There could be more plans. They cannot be gotten by just looking at the fixed formulation. So can we get the optimizer to get those other formulations? Is it what you're asking about, right? That's the core of the talk, yes. So that's really the question we're asking. So how do you use reformulation in the optimizer? Several ways, very interesting ways. So we have this modified query QM. It has this piece that I said we can replace by a pre-computed view, all the items that are just appliances. So if you have the syntactic test, maybe we can apply the syntactic test to this piece of the query and to the appliances view to see if they always produce the same answer. If the answer to this question is yes, then yes, you can replace this piece of the query by this pre-computed data. Does it make sense? And you know that you will always get the same answer. The second thing we can do with this reformulation is, if I'm giving you the second definition of my query, it's going to tell me if on all databases those two queries produce the same answer. If yes, then we can use QM to answer Q, right?
Isn't view also computed? Is view pre-computed?
Yes, it's a table. It's a table of all items that are appliances. And that table has a definition. And the optimizer, we want the optimizer to be able to use the definition of this table to see if it can replace the part of the query. Thank you. Yes, that's the challenge. It's so-called materialized views. So a view is just a query. It has a query format, right?
Okay, I thought, yeah.
So what you want to do for data analysis queries is you want to generate views that could be like pre-computed parts of a lot of the complex queries. So that means that a lot of the computation can be taken offline. You've pre-computed this view once, you can use it many times, right? And so this is the challenging one.
So why wouldn't you just say, instead of saying where exists in index in item, why wouldn't you just say where it exists in appliance table, like in appliance view?
Because we don't have this definition. We don't have this. We just have the definition Q. The question is, can we use this modified definition? This modified definition, it's a so-called expansion of this rewriting. The expansion of the rewriting, so you want to say, okay, I can answer this query using this view, right? Using this view, that means using the name of this view. So I have a reformulation of this query that says, okay, where appliances, right? Now, this is like comparing apples and oranges, because appliances is a new table. It's not mentioned in the original query. How do you know those guys are the same? So to compare the apples and the oranges, what you have to do is, it's a so-called expansion of the view. So you replace the name of the view by its definition in terms of the base relation. So that's when you're back to comparing apples to apples. Okay. So QM is actually this expansion of the definition using the view. Thanks a lot. Okay. So then, okay, somebody gives me at execution time for the query Q, somebody gives me its different definition QM and says try it instead. So my test would be able to say whether this QM alternative definition can be used to answer the query Q, right? So how can it be practically useful? Practically useful, it will become practically useful if the query optimizer also has a so-called query generator. So given the definition of Q, it produces other definitions that are guaranteed to always return the same answers. And this is what actual optimizers do. I have at least one pointer on the last slide that explains how actual optimizers, Microsoft SQL Server specifically, how it replaces parts of queries by views. Right? So for this, those questions need to be answerable. So can we solve the reformulation problem?
Who would write those views in advance? The analysts, the data analysts?
No, the data analysts are users of the database system. All they care about is give me back the answer to my question as fast as possible. So you have database administrators. Right. So basically what they do is they look for prevalent query workloads. They analyze those workloads. You can use an automated version of looking for those common pieces. For instance, Microsoft SQL Server claims to have this ability. So they do suggest definitions of those views that could be helpful in answering a lot of prevalent queries. And really, there is a lot at stake because those queries are very complex. Okay. So it is a very practical problem. Now, what we notice is that SQL is not very good for analyzing the syntax of queries, because SQL is just a string. You just type letters, right? You just type a sequence of letters. To be able to understand how two definitions are equivalent to each other, you should at the very least be able to reorganize each SQL definition. SQL does not work very well for this purpose. So what is used in database theory is the so-called data log syntax that really reveals the structure of the query. It is very similar to Prolog. How many of you have heard about Prolog? So very similar syntax. Okay? What it does, for instance, for the query Q, it says, take the table point of sale transactions with attributes store ID, item ID, date, and amount. Take the items relation, item ID name, and appliances. See, item ID is mentioned in the same way in the both tables. Okay? And then you have this funny set at the end. And then you say, okay, if you write this thing, then you get store ID and amount in the answer to the query. We will see how it works. Now, if we write in the same language data log, the modified query, it will not be an identical definition. But I hope you can appreciate how much easier it is now for us to compare the structures of the two queries. It's much, much easier. So the difference that we have in those two definitions is we have the different funny things going on between the curly braces. So they are not the same definitions. They are not identical, even at the level of structure. So how is it a structurally better definition of a SQL query? Same definition of Q as in the previous slide. Now, what the other thing that data log lets us do is we can write the stored data the same way. So this is basically predicate logic. So you say that you have a row in the point of sale transactions where the value of store ID is this store ID. Then you have this item ID for this transaction, this date when this item was sold in this transaction. And this is the amount of the transaction, right? So this is a piece of the stored data. This is a row of the point of sale table. Here's a row of the items table. For this item ID 371, it says that the name of this item with ID 371 is dryer, and it is an appliance. From now on, I'm going to abbreviate appliances because otherwise I can't bring, this into the same line. And so let's say that we can represent stored data in data log in the same way as queries. Okay? So we have 2 rows in the point of sale transactions table, and we have 2 rows in the items table. Okay? Now, how do we produce answers to this query? We can do it using the data log representation of the stored data and the data log representation of the query. We use so-called mappings. So here we have variables. All the uppercase letters are variables. So we say that if the stored data has an atom with this point of sale name, and it instantiates the value of store ID to this, it instantiates the value of item ID to this, and the same item ID can be mapped to a row of the items table, then this query produces the answer that takes this store ID, which is this, paired with the amount. That's how we, in data log, we produce answers to queries. Does it make sense at all? So that's a matching pair of 2 rows from the tables. Another mapping exists from the same query to other rows of the data. Now, if we use a mapping from S to this same store ID, from item ID to a different item ID this time, we find the matching in the items relation for the same item ID. And so what the query will produce is this store ID, the instantiation in this mapping, combined with this amount. Does it make sense? So on this database, because we have 2 matchings between point of sales and items on the same item ID, we will get 2 answers to this query. So we work with mappings here from queries to data. This is the beginning of our syntactic approach. So what are those funny curly braces about? That's very interesting. It works on the multiplicity of the answers. So the 2 answers that we got in the previous slide, they have 2 identical pairs of store ID and amount. So how many times should they be in the answer for this data analysis query? They have to be in the answer both times because those are for different item IDs. It's the same store ID, the same amount. For us to be able to calculate the sum correctly, they have to be in the answer both times. Does everybody see this? So how do we keep them in the answer both times? That's what the curly braces are for. So what happens here in this evaluation is that if we mention a variable in the curly braces, that means as many times as we change the values of some of those variables, that's how many times we get an answer, right? So that works on the multiplicity of the answer. Right? Same idea, same store ID, same amount for different items. Because the items are different, we have to produce this answer twice. So that's a very important point. If you have a different query, just to finish the explanation of the curly braces, it's a different query. It has empty curly braces. What does it mean for us in terms of the multiplicity of the answer to this query on the same data? This query has the exact same definition as the previous query, except for the curly braces. So we get the same mappings to the stored data, right? So that's the same as before, except that you have now no variables in the curly braces, which means we don't look at how many times we have different values here. And that means that for this query, you get the answer just once. That's the queries like this with empty curly braces is the data log representation of the queries in SQL that don't produce duplicates. That's the so-called queries with the distinct keyword. So we have the power in those curly braces. So how do we say that 2 queries with different definitions are equivalent to each other? What we are trying to do is to use the analog of the mappings from the queries to the data. Instead, we will be using those mappings between the queries. So what we want to form is we want to form a condition saying that two queries are equivalent if and only if you can find the right mappings from the first query to the second and from the second query to the first. That's what we're working on. And I hope that you can appreciate that at the SQL level, you cannot even start looking for such mappings. And that's why we have to have this representation. So here is our old friend, query Q. We've seen it many times. I'm going to show you an easier case first. So that's this same query in SQL, and then I added this exists condition. So the question is, are they the same? Syntactically, they're clearly not identical. It turns out that they return the same answers on all databases. How do we know? Using our mappings. We say that we map variables and constants from one query to the other and back. So conceptually, we say, okay, there is a mapping from this subgoal to this subgoal, right? Identity mapping. We have an identity mapping from this subgoal to this subgoal. And by the way, the curly braces also match. So there is a mapping in this direction. Now, see what is different in this query is that we have an extra copy of this subgoal with different variables, right? So when we do the mapping from Q, we just ignore the subgoal. It's okay. Do we also get a mapping in the other direction? Yes. We can find the mapping of the variables in such a way that the mapping also works in the other direction. This is the syntactic test that we are looking for. So because we have found those two mappings, we know for sure that these two queries return the same answers on all the databases. So if I return now to the slide that has the SQL for those two queries, we have an important conclusion here. If we get a query like this, so maybe an application program has generated a query like this, it can be simplified greatly. But the execution of this query to answer this query will give us the same answers, right? So we are simplifying the structure of this query by executing this query instead. So that's what those mappings give us. So here's the formal equivalence test. Actually, there used to be separate tests for several versions of such queries, and they all turned out to be special cases of a more general case. So what it's saying is that for a certain type of queries, very common queries in practice, under certain conditions on those two queries return the same answer on all databases if and only if you have a mapping from the first query to the second and you have a mapping from the second query to the first. What is really amazing here, apart from the fact that the previous work folds into this more general framework, is that there are queries in this language that could be equivalent without satisfying those conditions, right? And that's why you have to say it works on the condition on the two queries. So those are really very interesting, complex beasts, those queries. Okay, so two queries are equivalent if and only if you have mappings in two directions. So how can we use this test? This is exactly what we've seen before, right? These were the questions that we were asking. So now we can answer those questions using this test. So when we're looking at the query Q prime, we have its where exists part. So that's the extra part that we could throw away, right, when we reformulate this query into Q. So we could say that the appliances view is equivalent to that piece. So that's one thing that this test gives us. The second thing this test gives us is that given an alternative definition Q prime that we've seen, we can determine that the two definitions are equivalent. Once we have determined this, then we are free to choose the structurally simpler definition because we know it will be more efficient to execute.
So here you're saying Q prime, you mean QM?
No. QM is much more interesting. No,
Oh,
you
okay.
cannot get an answer for QM.
Okay, the in part.
Q prime, I took Q and I added a piece of QM to Q. Okay. So here this test helps. Okay. It doesn't help with QM. That's the next part. Okay. So thanks for catching me on this. That was intentional. So here we can find a more efficient in execution version Q for the query Q prime. And if we are given a query Q prime, we can generate a more efficient version Q. This is so-called query minimization. So we can do all of those three things. next thing. Given QM, using this test, we can determine that those things are not equivalent on all databases, right? So Q and QM are not equivalent on all databases. That's what our test tells us, right? So I was cheating. I said that you can use QM to answer Q. That was not true on all databases. So what is going on here? A very interesting thing. Let's stop looking at all databases. Let's start looking at databases of interest. It's getting closer to the database that I have at hand. How can you look cheaply at the database that I have at hand, right? Not at all databases, but just those that I have at hand. So this is what we want, right? So our test is not giving us this. So it turns out that the query QM that I showed you, there was no cheating. It is actually equivalent to the original query on some databases of interest. And on some databases, we really want a test that says that they are equivalent on some databases, so that on those databases, we can use the more efficient execution plan for QM to answer the query Q. So some databases is really the keyword here. So how can we revise the reformulation problem? We can bring in this notion of some databases instead of all databases. So given the definitions of two queries, see whether the definitions are conditionally equivalent. And that means we somehow have to define our databases of interest. And we bring it into the test. And same as before, we cannot afford to look at the data when determining that the two definitions are equivalent. So we cannot get all the way back to our single database of interest just because it's too large. So we still want the syntactic equivalence conditions. So how can we use the syntax to see that on our database of interest, the queries are the same? How many of you have heard about the notion of a primary key of a table? Primary key of a table is an identifier in that table. So when you're thinking about the items table, for each item, there is a single name and a single category that's describing this item ID. So what we're saying is that there is a technical way of doing this in real database systems. It says, given the items table, don't store in this items table 2 or more rows for the same item ID, right? So for each item ID, at most 1 row. So at most one source of information about the name of this item and about the category of this item. This is so-called primary keys, right? It is specified technically by the database system on the table. And so then, as hard as I try as a user to insert into this table 2 or more rows for the same item ID, the database system is not going to let me do this. So this database will satisfy this constraint at all times, right? So it's not all databases. We can have a database where you have 2 rows for the same item ID, but it would not satisfy our constraint. That would not be in our world, in our database system, because in our database system enforces this requirement. No more than 1 row for each item ID. So that's our some databases. Okay. So on all data, it turns out that on all databases where item ID is a primary key of items, in this sense, the queries Q and QM are equivalent. So this primary key thing, it's dominant in commercial databases. You define, as a database administrator, as a database designer, you have to define at least 1 key on each relation, just to avoid duplicate rows, for instance, for descriptions of items, IDs, and so on. So it's just there. It's always there. It's not that I'm trying to make up a database where that would hold. It's true in all commercial databases. So this is so-called constraints on the stored data. So that means that some tables for items you can store in my database system, right? Those with the duplicates of the item IDs. That's what the enforcement does. So that's really our databases of interest. If we know that this constraint holds on my data, why do I want to look at other databases? It's good enough for me to have a test that says that the queries Q and QM on all my databases, all databases that can happen in my database system, always give the same answer. Does it make sense? So when we have such a syntactic test, that means that on our databases, we can safely use the definition QM instead of Q. But on all databases, it does not work. That's why the old test was also correct. The old test was also correct. It was saying that Q and QM are not equivalent on all databases. It turns out that they are not equivalent only on those databases that don't satisfy this requirement. So there's no cheating going on here. The old test is correct, but you want a better test, right? To get a larger search space of reformulations of your query to get more efficient executions. So how do you extend this? So here's our Q. This is our QM. What is the difference between those two queries? The difference is just in the curly braces. So basically, conceptually, because you have more variables in the curly braces here, you can get more copies of the same answer in this query than in this query on any database. Does it make sense? So remember, we removed all variables from the curly braces, so then we cannot get duplicates in the answer at all. Right? So the more variables in the curly braces, the more copies you can get of the answer. Now, if you have this primary key constraint, it turns out that you can rewrite Q on only those databases. Because some of those variables, they are somehow not independently variable. You know, they can't all accept independently many values. Does it make sense? So some of them are dependent on each other because of this primary key constraint. So specifically, the name, N is the name attribute of an item. You can have 2 or more names for the same item ID. So the name attribute is useless in those curly braces. But what I'm trying to do here is I'm trying to reason about names and item IDs. I don't want to do this. I want a syntactic test. I don't want to look into the meaning of those attributes. So how can I do this formally? The required mappings don't exist by the original equivalence test. The curly braces have to be the same. So on all databases, it doesn't work. But it turns out that when you use, without knowing the meaning, this primary key information, so name does not, the values of name don't change independently of the values of item ID, then you can formally remove name from the curly braces. So on all databases that satisfy this restriction, these are the same definition. And you can, there is a process called chase to convert this query into this query that really doesn't look into the meaning of those attribute names. It just knows that item IDs somehow determine the value of name. And so you can remove the name here. And when we get this, this is actually QM. So on all databases that satisfy the primary key, we get an identical definition of Q to our original definition of QM. And so we get the old mappings. We use the same idea of the mappings. It's just that we know that on all databases that satisfy the constraint, this is our definition of Q. And then we get the same old idea of the mappings. We have a mapping in this direction. We have a mapping in this direction. And so we say they are equivalent on all databases of interest. So all of this is somehow, you could say that there are subtleties here and it's not very straightforward. However, people in real, in implementing real database management systems, they really care about those things. And so tests like this for a very special case of this general case of queries are actually implemented in actual query optimizers. And what people do, they don't use those nice representations. They use relational algebra. If somebody has heard about relational algebra, this is a very procedural language, and so it's very hard to compare definitions in this procedural language, because if you change the order of operators in this procedural language, it makes it that much harder to compare the structure. But people really do care about comparing those definitions. They just do it at the procedural level. So we have the equivalence of the two queries for the databases of interest. So as I said, from Q you can obtain QP using a so-called chase process. So you use constraints on your databases of interest to change the definition of the query. And the invariant that you maintain in those transformations is you maintain equivalence to the original query on all databases of interest, but maybe not beyond the databases of interest, just on the databases of interest.
So if the curly braces had I, D, N, and for example, A also in there, and D was the primary key on POS, then this chase process would throw out the A as well as the N. So like,
A is appliances, right?
I thought A is amount. No,
A is amount. We were working on only the curly braces here. So
yeah, so what I'm saying is, suppose the curly braces also had the capital A
yes,
in there,
yes, yes,
and
yes.
D was the primary key, then the chase process would throw out N as well as A.
If D is present in the curly braces, yes, yes. That's
Yeah.
a very good understanding of this.
Okay.
Yes,
All right.
yes, yes. Thank you. And so what does the extended test give us? It tells us that QM is a good representative for our original query Q on our databases of interest that satisfy the primary key. It says that the definitions are equivalent, and we can build a query generator that will generate QM from Q, because it did generate QP from Q, and that's exactly QM. So we did generate QP from Q, which is QM. This is our generator. And this is very valuable for optimizers. And then you can use this plan that we saw in the beginning to answer our query Q. And that means that we found the most efficient way of answering the analysis query. Because formatting the analysis query is just one step beyond formatting the answer to Q. All you have to do is you have to compute the sum of amounts, transaction amounts, per store ID. And so once you have all the just the relevant rows, that's unavoidable, right? You have to compute the sum, but you compute it only over only the relevant rows. And here, you are looking at just the relevant data. As much, you can have as much as irrelevant data as you want. Its size is not going to influence the execution time for this query. And so this is what we talked about. So we looked at relational databases. Very simple, very straightforward representation of data as tables. This is actually how humans think about structuring the data. So you think about objects, right? What do you want to say about classes of objects? For an ID, you say that an ID has an item, a name, and a category. And that's the information that you store in your table. Optimizers are extremely important in commercial database systems, especially so for analysis queries, because those queries are very complex and time-consuming. A lot of data analysis queries have to be executed repeatedly, and so the stakes are very high in the industry. And so we saw first the reformulation of a given query at the so-called physical level. That means that we fix the definition, but we use different so-called access paths to the data in executing the query. And the most efficient way of executing our query is to not access irrelevant data. That's the whole purpose of indexes, for instance. You do not access irrelevant data. But there is only so much that you can do at the physical level, because the next thing you can do is so-called pre-computed materialized views, and they are actually used a lot in the industry. So you pre-compute frequent pieces of very important queries, and then you recycle. So this you amortize for the pre-computation in the repeated use of those materialized views in the queries. How do you incorporate those views into the execution of a given query? You cannot do this without the reformulation. You have to do this with the reformulation. And so these results are very formal. You know, I'm building on very well-known results in database theory. So it's a combination of previous results as special cases of this general case, and this is a large practically used subset of the SQL that is actually used in data analysis queries. And so those results are very important in practice for complex data analysis queries. This is the end of the talk. Let me show you the references. So these are the results. This is a 1977 result, somehow the cornerstone of database theory. This is for queries with, where the curly braces are empty. Then you have a special case where the curly braces include all the variables that you have in the query. And here you have a beautiful syntax, data log syntax, that allows you to express these two kinds of queries, and all queries in between any number of variables in the curly braces using data log. Right? So it turns out that you can build a general equivalence test for all kinds of those queries. This is the pointer to the work that is done in actual optimizers. So they do compare definitions, but at the procedural level. So that's Microsoft SQL Server. And this is a chase reference, how you can formally massage a query definition while preserving equivalence on databases that satisfy certain constraints. Thanks a lot.
With regards to the curly braces, so in this particular example where you had just a date and no time, perhaps if they were going to add up the amounts of the sales and there were two identical transactions on the same day, you'd want to actually duplicate that record just because two people bought the same dryer in the same day.
Right, so then you would include the time into the curly brace.
So they deal with that by having a more specific date with a...
Well, yes, I was thinking about this. Of course, it's not realistic to have, at most one transaction per date. But the trade-off is you put too much information into your table. So that was just a...
So that's something that has to be dealt with from the company's point of view.
Exactly. But the approach is exactly the same.
Okay.
I was just striving for a simpler schema of the table for the purpose of this talk. You're, of course, right.
Would it cause problems in your database, like for that particular database that you had, that duplicate results would show up? Does that...
You would need those to compute the total amount for all the transactions. Right. So suppose you have, in this store, you have 15 transactions this day, all with the same amounts. They're all different transactions. So you have to generate all of those duplicates. Right? And so you have to have certain variables, such as item ID, in the curly braces to generate those duplicates. So a variable that you move into the curly braces, that means that the variations in the values of that variable generates more rows in the output.
But I mean, with the curly braces as they were there, you'd be throwing out duplicate transactions where two people bought the same thing. So you'd be throwing out information that you actually wanted in there.
If you don't have the curly braces.
No, I mean with the curly braces that you had. Two people bought the same item with the same item ID. They bought the same exact dryer. One in the morning, one customer in the morning and one in the afternoon.
Okay, so something has to be different between two transactions, right?
Right.
So there is a granularity of resolution somehow. So if you have two rows in the transactions table, there is also a primary key on transactions, and that means on at least one column, these two transactions have to have different values. So maybe it's the different times of the transactions. So if you have two registers, and they can produce two transactions at the same time, there's got to be something else. There would be a distinguishing factor, so that those two transactions are recorded separately in the database. Right? They have to have at least one column different value. That's how databases work. That's a very good point. Does it make sense? And then I would bring that variable into the curly braces, and it will work out. Right. Thank you.
What I didn't understand, some minor point though, was why Q had I, D, and N in the curly braces, and why the other one didn't have the N in there?
This is the where exists clause. The where exists clause says if there is at least one row with those properties, then that's all I care about. I'm not going to count the number of those rows. This is how the exists clause works. And so you can't have those variables in the curly braces because they don't influence the multiplicity of the result.
Can we see the query again?
Sure.
Q and Q.
I had them side by side somewhere, right?
I think it's much further now. Did we just pass it?
Right. So let's look at the data log version. So QM says there exists at least one row in items. There exists means that I'm not looking at the multiplicity of this here. In fact, if I look at the multiplicity here for a lot of queries, that will give me the wrong multiplicities of the answers. So that's how the where exists clause works. At least one row. If there is at least one row in that table, that means that the exists clause evaluates to true. If you have 2, it will still evaluate to true. If you have 0, that's what it will evaluate to false.
So in this work, given a database and a particular organization, we're trying to determine what is the best way to ask a query, right? So I'm wondering about the other direction. if there is any research in that other direction, where if you have a statistics of queries, then you want to automatically determine what would be the best organization for the database.
Yeah, that's a wonderful question. Did everybody hear the question? So given the knowledge of which queries are asked on the data, how to organize the data the best way. And that's the so-called view selection problem. So you look at the queries and you say, okay, you want those pieces pre-computed. How about I just express those queries in terms of those pre-computed pieces, so they become the base tables, and that will become the original structure of my data. Yes, there is work in that direction. It's somehow coming from different directions, yes, into the same place, yes.
So now I understand why the QM doesn't have name. Why does Q have name?
That's because it's a direct join. It's a direct join. It has bag semantics. That means that the multiplicity of all the variables matters. It's just a direct join without the distinct keyword. You've taken my course, so that's why I keep referring to those things.
So, but why doesn't it have amount then?
The amount is in the answer. They had variables, the variables that go into the answer.
Okay.
You get those values in the answer. The question is how many copies of each you get. And that's influenced by the so-called non-head variables, the variables that don't go into the answer.
Oh, okay.
So you have this dichotomy.
Okay.
Either you get a variable in the answer or it influences the multiplicity of the answer.
Any other questions? I have a question. Excuse my ignorance on this. Has category theory applied? It seems like this is a prime candidate for category theory.
I've never seen a use of category theory in this, so maybe that would bring, fresh blood into the area. I have to look into this. I haven't thought about this myself.
Any other questions? Okay, if not, let's thank our speaker.